So hello guys, welcome. Today in this session, I'm going to teach you guys the tricks of DFS which no one ever taught you, and you'll never find these tricks anywhere else. Okay, I have come to the conclusion, and I found these tricks after lots and lots of analyzing and years of experience in problem solving. So let's get started. What is DFS? Okay, the full form of DFS is depth first search, right? So just like write it for formality, depth first search. It means that we are going to travel the graph using depth, like the height or depth technique. Okay, so say you have this good looking graph, guys. Okay, node number 1 is connected to node number 2, node number 1 is connected to node number 3, node number 2 is connected to node number 4, node number 4 is connected to node number 8, and 2 is connected to 5, 3 is connected to 6, 6 is connected to 7. So this graph is clear to everyone, right? Now, how will we travel this graph using DFS? Always remember the super important trick of DFS. DFS. No one is going to tell you, I'm telling you that. Basically, you go to each branch from the root node and exhaust the searching there. Come back and do the same process with other branches till they are done. It means when you are at branch at node 1, you check which are the branches. There is one branch at 2, one branch at 3. So first you select the branch number 2 in DFS, exhaust this branch, then you select the branch number 3 and exhaust this branch. Okay, whenever you want to write the DFS order of the graph, always try to go boundary wise. If you go boundary wise, you can write the DFS order of the graph very easily. So let's say we have this graph. We have this graph here. 1, 2, 3, 4, 5, 6, 7, 8, 9. Now if someone tells you, tell me the DFS order of this graph. So you first always start from here. Okay, then you start making the boundary. See, boundary is like this, right? You start make going in the boundary wise order. This is the boundary, like this. See, this is the boundary. Just try to make the boundary of the graph. So guys, once you have made the boundary, you can easily write the order. Which comes first? 1, then 2, 1, then 2, then 3. Then we start, go back to 2, but 2 is already written, so ignore it. Then 4, then 5. See, I wrote the boundary, 5. Then 6. Then I go to 4, but it is already visited, ignore it. 2, already visited, ignore it. 1, already visited, ignore it. 7, good. Then you follow the boundary, 7, then it goes to 8. You follow the boundary, first it again goes to 7, which is already visited, ignore it. Then it goes to 9, good. After going to 9, it goes to 7, but it is already visited, ignore it. It goes to 1, it's already visited, ignore it. And this is our DFS order. Always remember this trick, guys. In DFS, just make the boundary of the graph, and that boundary is nothing but your DFS order. This was the single most important trick to know in DFS. Okay, so let's say we have this graph. Okay, guys, clear? So what will be the DFS order of this graph? What is the boundary? Boundary is something like this. See, I'm keeping my mouse. Okay, I am going from here. See, this is the boundary. Then like this, then like this, then like this, like this, like this. So the DFS order will be 1, 2, 4, 8. What will be the DFS order? It will be 1, 2, 4, 8. It will be 1, 2, 4, 8. Then again 8, 4, 2. But 8, 4, 2 have been visited, so ignore it. Then 5, 5 coming for the first time. So 5. After that, after 5, then again the boundary goes up. 2 is already visited, ignore it. Then 1, it's already visited, ignore it. 3 coming for the first time, we write a 3 here. And after 3, 6, we write a 6 here. and after 6 we again get 3, but 3 has been visited. We don't write it again and again. Then 7, 7 coming for the first time. Good, nice, great. Once 7 comes, you again go to 3, it's already been visited, ignore it. Then you go to 1, it's already been visited, ignore it, and it's over. That's the DFS order, guys. Okay. Now, how do we code up? How do we do the coding of DFS? Okay, we can just use simple recursion to exhaust the search space. Okay. So, for example, let's say, always remember this is the simple trick of DFS. What is the simple trick? The graph might be very big, so ignore it. Okay, there might be a branch here, a branch here, branch here, branch here, branch here, and let's say there is some stuff here. We call it as S1. There are some nodes here. Okay, then there are some nodes here, S2. Let's change the color now to, let's say, black. Let's say there are some nodes here, S3. Let's say there are some nodes here, S4. Now let's use a blue color. Let's say there are some nodes here, S5, and you're at node number 1. So whenever you are doing DFS, first pick this node number 1 and print this node. Once you are done with printing this node, go to the first branch and do the DFS on full all the nodes of this branch. Got it? Once DFS of this branch is done, then do DFS of S2. Then do DFS of S3, then do DFS of S4, then do DFS of S5. This is the general algorithm. What is the general DFS common? General DFS algorithm. No one will teach you in this manner. General DFS algorithm. What is it? Let's try to focus. So guys, general DFS algorithm, you take the source node, you print it. Let's say our source node was 1. We print it. Okay. Then you check and exhaust all the branches connected to source node. Then all you do is go to the different branches and do the DFS there. Then you check and exhaust all the branches connected to source node and do the DFS there as well, and do the DFS there as well. As you are repeating the same process again and again, it is using recursion. As you are repeating the same process again and again, it's using recursion. Okay. Recursion uses a secret stack space which is not seen to human eyes. Recursion uses secret stack space memory that we will explain you later. Okay. Now, so guys, recursion uses secret stack space memory, but you should know that you are trying to do the DFS again and again. How? I can explain you that. So the DFS algorithm is pretty much clear, right? So let's say I have a node here. Okay. Then I have these so many branches, guys. Okay. And now these are also having the branches, right? So what will the DFS algorithm do? Let's say this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Let's say this is 12, 13, 14, and 15. Okay, now what will this is node number 1. Now what will our DFS algorithm do? First it will take the node 1. Okay, it will print 1 in the answer. Now it will go through the branches, guys. Which is the first branch? First branch is this one. So we will consider the rest of the branches later. First branch is this one. Which is the node here 2. We will run the same algorithm of DFS on this much part. Considering this is our root node now. So what is the DFS algorithm again? First you print the given node. Then you go through all the branches. But which is the first branch? Which is the first branch? It is 3. So you come to here, you write 3, but when you come to 3, you see there is no other adjacent branch. No adjacent branch, no new nodes, only one branch is there, that is again the same node, so there is nothing left here. So you come back to 2. Okay, now which is the next branch? 4. So you do the 4 stuff. You exhaust and you see there is nothing there. You again go to 2, the next branch 5. You write a 5 here. But once 5 is done, you again treat it as a separate entity. Now, when you are at 5, what you should do, print 5 and see the branches. There is 6 is the branch, 7 is the branch. First go to 6, then do the 7 stuff. So once you are done with this, you are done with this also, done with this also. Now you guys remember we completed this branch, now it comes to this branch turn. So you print these guys. So after 7, it will be 8, 9, 10, 11. This branch also done, now you come to this branch. This branch will be 12, 13, 14, 15. So that will be the DFS order. I hope you guys understood how I am doing DFS under DFS by using the recursion trick. Like I'm doing the same thing on the same nodes, assuming that this is the first time we are looking at this node, just like the root node. Okay. So the algorithm remains the same, guys. What is the algorithm? That you have to take the source node. Okay. You print that node. Then you check all the branches connected to the source node line by line. You take the first branch, you do the DFS there as well, assuming assuming that again the top node of this branch is source node, and do the same thing again and again. Okay guys, I hope this much is clear. No one else in the market would explain you like I am doing such in-depth knowledge for such a low cost. Anyways, so guys, this much is clear. Now I think we should look at the codes, right? C++ code, Java code, Python codes. Let's have a look at the C++ code. The algorithm remains the same, so please try to understand even the C++ code. So we have this graph G, right? We take all the edges. Okay, the edges, first we read what? The number of nodes are 8, then the number of edges 7. So n is the number of nodes, and m is the number of edges, and I declare the graph. I read all the edges u to v, u to v, g. I want to make undirected edges, right? U is connected to v and v is connected to u. So g of u dot pushback v and g of v dot pushback q. Once this is done, I declare large arrays or vectors named as used and parent. What is the meaning of used? Used is nothing. It will used of I just means that the node I has been visited or not. Okay, guys. So I love Oshi. Oshi. So guys, similarly, parent means what? Parent means you are say currently at a node X. So we want to know from which node did you come here. That node is the parent. Okay. So basically, in this case, 1 is the parent of 2. 3 is the parent of, sorry, 2 is the parent of 3. So whenever you are going in this DFS order now, you want to know which node was just above you, that is called as the parent, from where the DFS came, just to know the history and the ancestorship. Okay, always remember these tricks, guys. Always remember these tricks. Okay. So that's it, and yeah. So guys, once I have that, I just put the first node in DFS. I also send the graph and the used and parent vectors or arrays, whatever you want to say. So guys, the algorithm remains the same. First you print the node. See, I'm doing that only. In the DFS, this node is 1, right? I'm printing that node on line number 8. Then I go to the next line. I write used of node as 1. It means that that node has been visited. That's why I'm setting that as 1. Used of node is 1. Once that is done, I will check all the branches. Okay. So if I write for auto u g of node, this will iterate all the branches. If I write here for auto u g of node, right? So it will look like this. It will look like this. For auto u g of node will look like g of 1. So guys, these values which you are going to come will be what? It will be 2 and 3, 2 and 3. How? First you will come to 2, then you will come to 3. You're trying to iterate all the branches, right? The nodes directly connected to node 1. So that is 2 and then there is 3. So there comes 2 and there comes 3. First there comes 2. So we check if used of equal to, if used of 2 is equal to 0, is that child never been visited, only then you should do DFS there. If this node slash branch has never been visited before, just go into it and search it using DFS and recursion. So I just first fix up the parent. So u is 2, right? So parent of 2 is node is 1, so parent of 2 is 1. Okay, I did that. Then I write the DFS again, it goes into recursion. I write, now start doing DFS at this node, DFS on 2. Now, once you come to 2, you start doing DFS on 2. Got it, guys? Got it? And once the DFS on 2 is done, all this will be completed. 2, 4, 5, 8, everything will be done. Once this is done, then you will come to 3. Then you will become 3. Got it? This is the trick. So, once you come at 2, you again iterate the branches, you will get 4 and then you will get 5, right? You will first print the 4, then you will do. So how will the flow go, guys? How will the flow go? Flow of DFS. First we will be calling DFS of 1, guys. Once that is done, we will be calling DFS of 2, guys. Okay, DFS of 2. Then DFS of 2, it will again be saying explore this branch and this branch, but this turn will come first. So DFS of 4. But when you are doing 4, it will say ki bhai please check the things below 4 also. So then in the will it will come as DFS of 8. Now as node 4 is fully exhausted, surged. Now, guys, everything for the 4 stuff is done, even the 8 is done. Now they remember the old stuff that you have to do this branch, then this branch. So now you will do branch number this 5. So DFS 5. DFS 5. Okay. DFS 5. Okay. Now, uh, then this 2 is already done, so ignore that. And now we will remember the part where we were saying that you had to do this edge also and this edge also. So this was done. Now comes this guy's turn. So DFS of 3. Then, guys, DFS of 6. Then DFS of 7. So DFS of 3. Now, as node 2 is fully exhausted, surged, as guys that node is fully surged, so we write DFS of 6. Okay, guys, this is very very important. DFS of 3. Okay, because now the 2, now everything for this node number 2 is done, all the nodes below the node 2 and 2 are done. So now comes the time of this branch, node 3. So now we will do node 6, this one first, and then 6 is all done, then 7, then it's all over. DFS of 3 and DFS of 6 and 7. DFS of 6 as node 6 is fully exhausted. So DFS of as node 6. I'm just writing this line somewhere, sometimes in middle. Searched. So DFS of 7. Okay, guys. Now, whenever you are iterating, now this iterator, this gave you all the nodes which are directly connected to node number 1. So why am I writing this condition if used of u equal to 0 only then do DFS? Because it can sometimes happen that the same nodes come into the picture which is already been visited. For example, when you are at say node number 5, okay, now you try to iterate all the nodes which are connected at node number 5, then only 2 is connected. But doing DFS on 2 is not useful. Why? Because DFS on 2 was already done, then our number of DFS 5 came. So DFS of 2 was 1, that's why I set it as used of 2 as 1. So I will only go to the node if the used of that node is 0. It has never been visited again. It has now been visited. So guys, this much in-depth explanation no one in the world would give you, which I'm doing for you guys. Okay. So please take the benefit of it, utmost benefit. So let's check the things. Okay, nice. Good. Now, this much is over, guys. Now let's talk about the final thing. Is we are doing recursion, right? Again and again, calling the same function, but this is using a secret stack memory which is being used by the compiler. So how does it look? I will tell you. So guys, DFS uses a secret stack. Okay, so explaining about the secret stack to everyone. Secret stack. Okay, so uh, secret stack. So what is the secret stack? So guys, all the nodes which we were traveling get stored in the stack. All the nodes which we were traveling gets stored in some stack. So guys, how does my stack looks? First it looks like this, then you do BFS of 1, so stack looks like this. Okay, then you do then you go to DFS of 2, right? You go to DFS of 2, right? So stack looks like this, 1 and 2. 2 is the topmost node of the stack. 2 is the topmost node of the stack. Then yeah, so once that is done, we go to which node? Node number 4. So stack looks like 1, 2, 4. Stack looks like 1, 2, 4. 4 is the topmost node of the stack. Then you go to node number 8. So stack looks like this, 1, 2, 4, 8. Such detailed explanation, guys. I would be so lucky if someone explained me during my times. Anyways, 1, 2, 4, 8 is done. Now, guys, you go back. You go back. So now 8 you have visited and will never visit it again. So you remove the node number 8 from the stack. So you come to 4 again. So now the stack looks like this. Now the stack looks like this. You remove the 8. Now that is done. So now you again write the stack. Now you come to 1 to 4. But even 4 is done. So now you remove 4 also from the stack. You again come back to 2. So now it will look like 1 comma 2. Now once all that is done, you will go to 3. So stack will look like 1 comma 2 comma 3. Now 3 is also done. So remove it now. Stack is 1 comma 2. Okay, 3, not 3, sorry, this is 5, 5, 5. Sorry, guys. You went to 1, 2, 4, 8, then you remove 8, remove 4, you again go to 2, now you go to 5. So this is 5. 1, 2, 5. You visit 5, you are good, done with it. Now kick out 5. Now it's again 1, 2. Now it is confirmed that you visited all the children of node 2. So now you can successfully kick it out. You can only kick out the node from stack if all its children are visited. Okay guys, see the node number 2 which we had, its children are what? 4, 5, 8. Unless and until all these are visited and removed, you cannot remove 2. Okay, so now 2 is also done. Now we come to 1. So now stack looks like this. 1 will only be removed when the full graph is completed. Common sense. So stack looks like this, guys. Now how will the stack look like? Now the stack will look like It will come to 3. Okay, then now it's simple, guys. 1, 3, then it will go to 6, then 6 is visited, 6 will be removed. So it will be 1, 3, then it will look like 1, 3, 6. Now 6 is done. You can remove the 6 because all the children of the 6 and 6 have been visited. Okay, so one kick off run if all its children and that node itself. So 6 and all its children have been visited, kick them out. So stack is 1 and 3. Yeah. Can you kick out 3? No. Because all children of 3 are not visited. Only 6 is visited. 7 is left. So 137. Stack is 137. You can kick out 7 because 7, you can now kick out 7 because 7 and all its children. There is none. There is no child of 7, by the way. Have been visited. Have been visited. Okay. Similarly, now you kick out 7 and you write stack 1 comma 3. And the same reason you can write, let's cut this for 7 because this is very basic. Now stack will look like this, guys. Now we will be kicking out the 3. Why? You can kick out 3 because 3 and all its children, there are children of 3, 6 and 7 have been visited. Now it looks like this. Now the stack will finally be empty. You kick out 1. You kick out 1. You kick out 1 because all nodes have been visited. I will not write that you have visited 1 and all its children. It's common sense. Okay, guys. That's it, guys. You got the golden knowledge. Anyways, now let's try to focus more. Mm, mm. Okay. So now what were we? Let's check some of the different implementations. The C++ one is clear to everyone, right? So now let's quickly go to the Java implementation. You guys can check. It is just same public class main. Okay, everything is simple. You do the exact same thing. Okay, you first take n and m as input, then you read the g. Okay, the list graph which you are creating, then g of u dot add of v and g of v dot add of u, and take the input of those edges. Once the input is done, declare the used and parent arrays or list, whatever you want to call. Then initialize all the stuff inside them with 0. I've written n plus 5 just for fun. You can write n plus 1 also because I'm using 1 based indexing. Then you call the DFS function which starts from node number 1. Now from which node you have to do DFS, it's totally your choice. Okay, I've used a tree as a graph in this example for better visualization. Now guys, the algorithm is same. You print that node, you set that used of that node as 1. If the used of that node is 0, you print that node again and you again do the DFS. Okay, that's it, simple. Whenever you do DFS, a secret stack is created in the recursion which is not visible in the code, but compiler uses it. That's why I explained what is compiler doing at the back when we are doing recursion. Okay, similarly guys, Python code very very easy. Now the time complexity of this code is not hard, it's very very easy. You are like going through all the nodes and edges, right? So the time complexity will always be what? Time complexity will be what? The number of nodes plus number of edges. Time complexity, time complexity will always be because you are iterating through all the nodes and all the edges of nodes plus edges. Now what will be the space complexity? This is interesting. The space complexity will be maximum depth of the graph, maximum depth of the graph from the source node. That's how large the stack can get. That's how large the stack can get. Guys, you remember that we were using the stack that was using space, right? So see what can be the maximum space the stack can use for our graph. It can either be of size 0, then 2 maximum. It can be of size 4. Okay, 1, 2, 4, 8. So that is maximum depth for our graph was, maximum depth of our graph was 4. Okay, now so guys, the space complexity is nothing but O of maximum depth of graph. Okay, it is also called as diameter. So O of diameter of graph. In general, diameter means the longest possible distance between the two nodes of the graph. So if your source node is one of those nodes, then it can go to that worst case, right? That's why I'm saying graph diameter of graph. Now this can in worst case be n, because you can create a graph like this, right? One is connected to two, two is connected to three, then it's five, then it's going till n. Okay. So here the depth is n. Depth is what? N. Right. So in the worst case, the space complexity can go to O of n. Okay. In the worst case. Okay, guys. That's how large the, now if you guys have already studied the stuff, like we will now be discussing the differences in the BFS and DFS space complexity. It in the worst cases both are the same, but depending on the different structures of graph, they both will give different results during the running. Okay, guys, this is simple. Python code very simple. Just declare the list. G of u dot append v, g of v dot append u. Then you print the node. Used of node is 1. Then the same thing. If use is 0, this that. Like it. Now, what does a breadth first? No, this is not true. So, guys, always remember whenever you are doing BFS, you are using a queue, and all the levels of the nodes are stored in the queue. Like the node 1, then the node 2, 3, then this level, then all the nodes at this level. So for a BFS, the space complexity will always be what? Maximum number of nodes at a particular level in the graph. So in this graph, maximum number of nodes are 1, 2, 3, 4, 5, 6, 7, 8 in the last level. So it will take 8 space in the queue. But for the DFS, it will depend on the height of the tree or the depth of the graph. So the depth is what? 1, 2, 3, 4. So if you do DFS on this graph, the space required is 4. But if you do BFS, the space required will be 8. So depending on the graph, in some graph, what can happen? That the height is more and the width is less. And sometimes it can happen that the width is more and the height is less. So please remember that you guys go through this. Okay, either search method can be written so that it has to keep only track of the but then the DF is more efficient. DFS only has to travel the nodes, it would be more the VFS as a travel of the tree. Okay, there are some more here and there also, but in general, like never say this in interview, but when you run the things in OA and CP, na, DFS works much faster, because in general, the height of the graph is always less than the width of the graph. Okay, na, in general, for most of the graphs which are n 10 raised to 5 nodes and 10 raised to 5 edges, generally it happens. Okay, so you can read this link. It contains lots of deep knowledge which you can explore yourself. Okay, guys, now Ram Ram. Now I think everything is done. Now let's close this session. Love you all. Take care. I love Oshi.